a lot of limits so far, and that isn't the end of it. We have another couple set of limits to go over to figure out how to solve. So far, we've done polynomials. We've done a little bit of trig with the squeeze theorem. And we've done, well, that's about it, right? So now we have some funkier limits that I kind of forgot to talk about so far. So we're going to go over how to do these. And I don't know why I try to make myself laugh and I forget about it, but we have some lyrics on the top, but that's not important. Okay, so we're going to talk about limits, how to solve limits of different types of functions. And we're going to start with the exponential type of function, okay? Exponentials, what are they? What's an exponential function? Exponentially increasing or decreasing, right? So any function that looks like 2 to the x, e to the x, 4 to the x, something like that with x in the exponent, that's when we have an exponential function. So we're going to learn how to find these types of limits, okay? Now, just a little reminder with limits, as long as we can plug in the number and get something that looks like something that works, we can always pretty much plug into any sort of function, kind of like polynomials, okay? So for example, the limit as x approaches 2 of e to the x plus 4, even though it looks weird, let's just try plugging it in. E to the 2 plus 4, that gives me e to the 6, right? Okay, e to the 6 is a number. It's not like infinity or 0 over 0 or something like that. We're okay. That's the answer. Okay, so a lot of times we can just plug in. Okay, sometimes we can't plug in though, especially when we have infinity as our thing that we're approaching. So let's take a look at these limits. Okay, so let's take a look at the limit as x approaches infinity of e to the x. Okay, maybe a graph might help us out here, right? What does the graph of e to the x look like? Yeah, Sam.
It's like constantly increasing, but there's like a horizontal asymptote. It's like 2.2 something.
I think you're talking about, it's not a horizontal asymptote. The horizontal asymptote's at 0, right?
Oh yeah.
Yeah.
Right.
I think you're talking about how E is made.
Yeah.
Yeah, but it actually looks like this with the horizontal asymptote at 0, and it kind of like increases exponentially, right? I think you're talking about like how
Yeah.
Yeah, the
I'm
limit.
just thinking of like the decimal. I don't know.
Yeah. Yeah, you're on the right track. I know what you're talking about. Okay, but we're increasing exponentially as we go to the right, and as we go to the left, we're kind of approaching the x-axis, but we're never touching it. Looking at the graph, what's the limit as x approaches infinity of e to the x? Not 0. As we go to the right, so we're getting really, really big numbers of x. What are we expecting the y value to be? Infinity, right? So as x values are getting larger, the y values are getting infinitely larger. So that's why the limit as x approaches infinity of our function is infinity, okay? Let's go to the bottom one here. What's the limit as x approaches negative infinity of our function?
0.
0, right? Because as we're going to the left, our function is getting closer and closer to 0. Okay, now let's kind of switch things up a bit, okay? What about e to the negative x? What would you expect the limit as x approaches infinity of e to the negative x to be?
Negative infinity?
Not quite. Now we can graph it. I hear 0. How'd you get 0?
Something to the power of a negative number is 1 over, like,
Oh, okay,
e
I
to the
see.
power of negative x is equal to 1 over e to the power of x.
Okay, that's smart. I didn't think about that, but yes, that is true. We could graph it and figure it out as well. Why don't we just kind of plug it in, but not circle it as our answer? Okay, why don't we just plug in? We're trying to find e to the negative infinity, essentially, right? Okay. So negative infinity is going to negative infinity. So we're basically looking at what e does, the graph of e to the x does, as we go to negative infinity, right? So without graphing the function, e to the negative x, if we plug in positive infinity, we're actually looking at what happens to e as we go to negative infinity. Can we see that that graph is going to 0 as we plug in essentially negative infinity? Okay. Let's make it even a little more complicated. What about e to the negative x as x approaches negative infinity? Well, why don't we plug it in? E to the negative infinity is e to the positive infinity. What does e do as we go to the positive infinity numbers? Infinity, good. Okay. So kind of confusing, but basically what we're doing is we know what e to the x does. We know what that graph looks like. Maybe I don't want to graph all these other funky functions. What if I just plugged in infinity or looked at what the exponent goes to and then figure out what e to whatever that is? Okay, and if that doesn't make sense, I think a couple other examples will kind of illuminate that for us. So basically what I'm saying is don't try to graph every single function that looks funky, okay? Know what the graph of e to the x looks like, and maybe we can see what the exponent goes to and plug that in to e. Okay, and let's do a couple examples that might make this make more sense. Okay, so my process here is I'm gonna see what the exponent goes to. Okay, so I'm gonna take my exponent, see where that's going to as x approaches whatever the number is. And then I'm essentially gonna plug in that result into e to the whatever. Okay, so I'm going to stick that in the exponent and see what happens. Okay, so example number A, we have e to the 2 minus 4x minus 8x squared, and we want to see what happens as x approaches infinity. Before we take a look at e, let's see what the exponent goes to first. So my exponent is the 2 minus 4x minus 8x squared. As x goes to positive infinity, where is the exponent going to? What is this guy going to? Okay, well, we have a negative quadratic here, right? We have minus 8x squared. That's kind of my overpowering term, right? I know quadratics look like a parabola, but when there's a minus in front of it, the parabolas go down, right? So that's essentially what my exponent looks like. As we go to positive infinity, where is the quadratic going? Negative infinity, right? As we plug in really positive large numbers into my exponent, where we have a negative x squared, we're expecting negative numbers to happen. Does that make sense? Okay. All right, I swear the next examples will make it a little bit faster, I promise. Okay, so I know that the exponents are going towards negative infinity. Let's plug in that value into e to the negative infinity. Okay, remember, e looks like this. So as I plug in negative numbers into e, where am I going towards? 0, good. Okay, so my answer to this limit is 0. Before we go on, is there any questions that we have on part A? Okay, I know this is kind of a hurdle to go through. I feel like it's a lot of steps, but I swear as we do more problems, it'll get easier. Okay, we have the limit as x approaches 0 of e to the 1 over x. Okay, let's do the same thing. Let's focus on the exponent first, and then we'll plug it into e. Okay, so the exponent is 1 over x, right? What is the exponent going to as x approaches 0?
Doesn't exist.
Doesn't exist, and you know what? Let me change this. Let's say we're going from the right. Now where is it going to? Infinity, right? Isn't the graph of 1 over x, doesn't it look like this? Okay, so as we go towards 0, the graph of 1 over x is going to infinity. Do we all agree on that? Perfect. Okay, so yes, I know we're approaching 0, but now we're going to approach, we're going to plug in infinity into e. Okay, because I found what the exponent goes to. Let's plug in infinity into e. What is e to the infinity? Infinity, good. Okay. Any questions on part B? All right, I'm gonna do 2 more and I swear I'll let you on your own. Okay, part C, same sort of question, but instead of approaching 0, we're approaching positive infinity, okay? So we're gonna take our exponent, which is 1 over x, right? What is 1 over x or exponent approaching as we go to positive infinity? 0, right? 1 over x is approaching 0 as we're plugging in really big numbers, right? So this is going to 0. If you're ever confused, you can always graph 1 over x and see where it's going, right? Okay. Okay, the exponent is going to 0. So we're going to plug in what our exponent is going to into e. We have e to the 0. What is e to the 0? 1, good. So this limit is equal to 1. Okay. One more. We have e to the t to the 4th minus 5t squared plus 1, and we're approaching positive infinity. Let's take a look at the exponent. The exponent is our polynomial. It's t to the 4th, right? Where is our exponent going to as t goes to infinity? Positive infinity, right? We're getting really big numbers if we plug it into a positive polynomial. So this is going to positive infinity. Let's plug in infinity into e, essentially. What is e to the infinity? Infinity, good. Okay. Okay, any questions on how I'm getting A through D? All right, why don't you give letter E and F a try? I know it's a little hard to conceptualize, but I think we can get there. Let's go through part E, and I promise you, if we're feeling uncomfortable, we'll do more practice on this, okay? Okay, so we have e to the 3t over t to the 4th, okay? The exponent is that fraction, right? And we want to see where that goes to, okay? I think I want to rephrase what how I'm saying this. I'm saying that the exponent is going to something. When I'm saying that, what I'm essentially saying, without saying it, is what's the limit as t goes to infinity of the exponent, okay? Okay, so that's essentially what I'm saying when I'm saying what the exponent is going to, okay? What is the limit as t goes to infinity of our fraction here?
0.
0, right? Very similar to our quiz. When the numerator, the degree of the numerator is smaller than the degree of the denominator, that limit's always going to be 0, right? That's something we did on our quiz. So our exponent is going to 0 as t approaches infinity. Okay, so e to our 0 power is what number? 1, good. Okay, so e to the 0 power is 1. 1 is our answer. Any questions on letter E? Does it make more sense when I phrase it as the limit instead of the exponent going to something? Okay. Okay, part F looks a little bit weird. The reason I put it here is because you might see this in the future when we're dealing with more complicated sort of things. Whenever we have a limit of 2 functions being added together, we can always break it apart, right? So I can always split this limit into the addition of 2 different functions, right? So this is the limit as t goes to infinity of e to the 2 over x squared plus the limit as t goes to infinity of 4 e to the 2 over x. Right, so now I have 2 limits that I'm dealing with. Okay, you can go even further and take the 4 out of the limit, right? So this is the limit as t goes to infinity of e to the 2 over x squared plus 4 times the limit as t goes to infinity of e to the 2 over x. Okay, So now we have limits that we can actually deal with. You can skip this step and do this in your head, but I think it makes it a little bit easier. Okay. Why don't we focus on two of the limits, or one limit at a time? Oh my gosh. Okay, so let's take a look at our exponent. 2 over x squared. Okay, when I'm saying what the exponent goes to, I'm saying what's the limit as t goes to infinity of my exponent, 2 over x squared. What is that limit? 0, right? The denominator has a really high power. The numerator doesn't even have a degree. Basically, the degree is 0. So that limit's going to 0, just like we did on our quiz. So this exponent's going to 0, okay? So the limit of e to the 2 over x squared is basically e to the 0, right? And what is e to the 0? 1, good, okay? So the answer to this limit is 1, okay? Okay, let's do the limit as t goes to infinity of e to the 2 over x. Let's take our exponent, which is 2 over x, right? What is 2 over x going to as t approaches infinity? 0, good. Okay, so if I want to find the limit as t approaches infinity of e to the exponent, my answer is also going to be e to the 0, which is 1. Okay, so I found one limit, I found the other one. Let's add them together and multiply that 4. Looks like we're left with 1 plus 4 times 1, okay, which is 5. Okay. Any questions on part F? Okay. Do we feel like we need a little more practice with the exponential functions? How about this? We'll do some more tomorrow. I feel like maybe some extra practice might help us out a little bit. So we'll do some more of this. But let's move on to logarithms. Same sort of deal, but just a different function. Okay, logarithms. I feel like this is the thing that scares everyone because everyone seems to forget about logarithms after a while. Anyone want to tell me what the graph of a logarithm looks like? Yeah, it's like e to the x, but it's flipped upside down, right? It's the inverse, good. So if we have the x and y axis, instead of x equals, or the x-axis being our horizontal asymptote, we actually have a vertical asymptote at the y-axis. And it kind of looks like the exponential function, but it's flipped upside down, okay? So we're getting closer, are you okay? And we're getting closer and closer to the y-axis, and we're kind of exponentially increasing as we go to the right. Okay, taking a look at this graph, what's the limit as x approaches 0 from the right of ln x, which is the natural log, right? What is that limit going to?
Negative infinity.
Negative infinity, right? As we're getting closer and closer to 0 from the right, our y values are getting closer and closer to negative infinity. What about as x approaches positive infinity? Where are our values going now? Positive infinity, good. Okay, this is basically all you have to know. Okay, you don't have to know what the graph of all the different log functions go to. As long as you know the basic function, the basic shape of a logarithm, you should be able to find these limits. Okay, so let's go through a couple of these. Okay, the process I use for this is very similar to my process for the exponential functions. Okay. But instead of seeing what the exponent goes to, I'm going to look at what the inside of the logarithm goes to, okay? So here are my steps. I'm going to see what the inside approaches. Okay, so I'm going to see where that goes. And then I'm going to plug that into the log, essentially plug it in. Okay, plug that into the log. Okay, so kind of like a two-step process, just like my exponents. Okay, so we have our log of 7t cubed minus t squared plus 1, and we're looking at where that goes to as we get really, really large values as t approaches positive infinity. Okay, so first what I'm going to do is I'm going to look at what the inside goes to. Okay, and when I say look at what the inside goes to, I'm essentially finding the limit as t goes to infinity of the polynomial in the middle, 7t cubed minus t squared plus 1. Okay, what is that limit? Infinity, right? We have a big polynomial, there's no negatives going on, that's going to positive infinity. Okay, once I find that limit, I'm just going to plug it in essentially, or find the limit of log of infinity, okay, essentially. And what is log of infinity? Infinity, right? Just like we found up top, as x approaches infinity, our log is going to infinity. Okay, I know my notation is kind of bad, but this is my thought process. Any questions on part A? All right, part B, we want to find the log of 1 over t squared minus 5t as we're approaching infinity. Let's see what the inside goes to. Okay, remember when I'm saying where does the inside go to, I'm essentially finding the limit as t goes to infinity of the inside. Okay, what is that limit? 0, good. Okay, so now once I found what the inside is approaching, I'm plugging it in to the log. Okay, and I know here's where things get a little tricky. I'm not essentially plugging it in, I'm looking at where it's approaching. Okay. Okay, so I'm plugging in 0, but I'm not finding the y value. Where is log going as we're approaching 0? Negative infinity, right? So I'm not essentially plugging in 0, I'm seeing where log goes to as I approach 0. Any questions on part B? Okay. All right. I think I feel pretty confident with C and D. I'm going to give you a couple minutes to work on C and D, and then we'll come back in a tiny bit. I think some of you are still working, but that's okay. Let's look at part C, okay? Now, when we're looking at log limits, we want to find what the inside's going to first, right? And whenever I say what the inside's going to, I'm technically looking at the limit as t approaches, infinity of the inside, t over t plus 5. What is that limit? 1. And why is it 1? Good, right? The degree on top is 1. The degree on the bottom is 1, which means the highest power. Since they match, we take the coefficients of the highest power. 1 over 1 is 1. So the inside is essentially approaching 1. Okay, now we can essentially plug in 1, log of 1. Okay, we're essentially plugging it in to our log. Where is that going to? 0, right? Now, if you ever get confused, you can always just type it into your calculator. But the log of, log base anything of 1 is always 0. Okay. Any questions on part C? Okay, let's do part D. Remember, part D, we want to find what the inside is going to. Essentially, what's the limit as n approaches 0 from the right of 1 over n? What is that limit going to? Infinity, good. Okay, so the inside's going to positive infinity. Okay, let's plug it into our ln. What's ln of infinity? Where's that going to? Infinity, right? If we take a look at our log graph, as we plug in really, really big numbers, we're getting really, really big answers. Okay, so the answer to part D would be infinity. Any questions on part C or D? Oh, Troy? Yeah, do you see how the inside is going to infinity?
1 over n.
The 1 over n? Yeah. Let's figure out how the 1 over n is going to infinity. Okay. So when I say the inside, we're basically finding the limit as n approaches 0 from the right of 1 over n, right? Okay, the graph of 1 over n looks like this, right? So as we approach 0 from the right, can you see how the y values are getting really, really big? Yeah, so this is why the inside's going to infinity. Does that make sense so far? Okay, good. So once we're here, we can essentially plug in or see where the log's going as we're approaching positive infinity. Okay, now the graph of log looks like this. Okay, so as x values are going to the right or towards positive infinity, where's the log going? Not 0, right? Because we're looking at the values of x as we get closer to positive infinity. The y values are getting closer and closer to positive infinity, right? Do you see it now? All right. I know this is kind of mental gymnastics, right? We're trying to see what one function goes to, and then we're plugging that into another function and seeing where that goes to. A lot of things to keep in mind. My best advice to you is if you have a graphing calculator, might take some edge off to the question if you can see what the functions look like, especially if you tend to forget what log or 1 over x or stuff like that looks like. Okay. Any questions before we move on? All right. We're actually going to move on to a different type of limit. We're going to stop the mental gymnastics and actually go to things that we can actually algebraically work with, which is a little bit easier for us. And we're actually going to go to trig. We're going to talk about these limits. Now, we have talked about limits before that involve trig functions, but the only way we've dealt with trig functions were with the squeeze theorem, right? We had, we would take our function, know that it's between like -1 and 1, and do a bunch of stuff with it until we found the limit. Okay, we're going to talk about how to do other fancy trig limits that don't involve the squeeze theorem. And we'll talk about how to do these guys, okay? Before we get into these types of questions, I need to tell you 2 things that you have to memorize, okay? There are 2 very special trig functions or trig limits that there are proofs as to how they work, but I'm not going to go over them. The 2 of them is the limit as we approach 0 of sine x over x, okay? That limit is equal to 1. Okay, so that's a limit that you have to know. And then another one is 1 minus cosine x over x. Okay, that limit goes to 0. Okay, so it doesn't have to be x that's plugged into. We can plug anything into sine over the same thing. As long as the limit's going to 0, that limit's going to be 1. Okay, so it doesn't have to be sine x over x. It could be sine of smiley face over smiley face. Okay, as long as the thing inside the sine and the denominator match, that limit's going to 0. Same thing with cosine. As long as the thing inside of the cosine and the denominator match, that limit is also going to 0. Okay, so it doesn't have to be x. Okay, so here's a small example. We have the limit as x approaches 0 of sine of 6x over 6x. Since the 6x matches inside the sine and in the denominator, what's this limit going to be? 1, good. Okay, so as long as the inside of the sine and the denominator match, that limit is definitely going to be 1. Okay. Okay, let's take a look at this example. We have the limit as x approaches 0 of the sine of 4x over x. Now we have a little bit of a different situation now because the inside of the sine doesn't match the denominator. 4x doesn't match x. Any ideas on how we can make it match?
Take out the 4.
Can't take out a 4 out of the sine because you can't take something out of the inside of a trig function out, but that's a good idea.
Multiply by 4.
We can multiply by 4, but I can't just take a limit and multiply it by a number, right? Divide by 4, okay. Do you want to combine your 2 answers?
Multiply by 1 over 4.
Okay, multiply and divide by 4, right? You're essentially, I see where you're going here. You can multiply anything by 1, right? It stays the same, okay? So maybe instead of multiplying by 1, I can multiply by a different version of 1, right? So let me do something real funky here. sine 4x over x, okay? But instead of writing 1, I'm going to write a different type of 1, which is 4 over 4. Okay, so you're real close. You just had to combine your two answers. All right. And the reason I chose 4 is because I want the denominator to be 4x because the numerator has a 4x in it, okay? Okay, so let's see what we can do here. The limit as x approaches 0, we've got 4x in the denominator and we've got a 4 sine of 4x on top. Okay. Now we're really close to what the memorization thing that we have to do looks like, right? We know that the sine of 4x over 4x, the limit approaching 0 is going to be 1. What can I do to make this limit look like the formula?
Take the top 4 out of the numerator.
Yeah, right. You can take the top 4 out of the limit, right? Or out of the numerator. Okay. So maybe instead of writing this, I can write 4 times the limit as x approaches 0 of sine of 4x over 4x. Okay. So you can always take a constant out of the limit, right? Okay. Well, that limit is, well, what's that limit going to be?
0 or 1.
Not 0, but 1, right? This limit is the thing we have to memorize. The sine of anything over the same thing as we approach 0 is always going to be 1. So 4 times 1 is 4. That's right. Any questions on example 6? All right, how about this? Example 7 is very similar. Try that one. I think it's a slightly different, but I think you might be able to solve this one. Why don't we go through example 7? I think example 7 is similar to something, maybe not. Okay. Okay, example number 7, I know some of you still working, that's totally fine. But let's just take a look at what this one says. Okay, we want to find the limit as t goes to 0 of this crazy function with a sine of 3t and a t on the bottom. Looks really similar to our first formula with the sines, right? We know that the sine of something over itself is going to 1, but I need the denominator to match what's inside of the sine, all right? I want to multiply by something, maybe a glorified version of 1. What did you decide to multiply by? 3 over 3, right? I have a 3t on the inside. I have a t in the denominator. Maybe I should multiply by 3 over 3. Okay. Okay. So this would turn into limit as t goes to 0. Looks like I have a 12 on top, sine of 3t. I've got a 3t on the bottom. What can I do now? Yeah, you can take the 12 out, right? Now, sine of 3t over 3t looks like something that we know how to do. So if I take out the 12, then it looks exactly like the formula, okay? So we have 12 times the limit as t goes to 0 of sine 3t over 3t. Okay, well, what's the limit of sine of 3t over 3t? 1, good. So this becomes 12 times 1, which is 12. Okay. Any questions on example number 7? All right, I'm going to let you go early. We'll start with example 8 next class. We'll do more examples with the exponentials so we feel a little bit more comfortable. And I'll see you on Wednesday.